power at F. This is F. To calculate the power, we have two options, and you choose. That's up to you, absolutely. Are you going to use the integration in time or summation in here using Parseval theory? Both will converge to same answer, but one of them usually is too difficult. The other one is so easy, and that is absolutely up to you. But you will learn by solving different homeworks and questions that which one you prefer. In here, I tell you, if you do this one in Parseval's theory and you go to Fourier series and you want to do a summation over all of those components, all of those coefficients, it's going to be a series which goes to infinity, right? And you have to have a good knowledge about series, which I assume not many people have that. But if we use integration here, it's just a square wave, right? It's easy to integrate it. So I prefer to use time domain to calculate power of F instead of Fourier domain. So I'm going to take that one and just do what we use as a base definition of power, right? Ft square dt. And period is 12, so 1 over 12. And I can break this integration into two parts. One is this, from here to here, and then here to here. And from here to here, 0 to 6, what is the value of the signals? Fixed, is constant, is only 2 over 2, right? dt. And the other is from 6 to 12. Again, but it's a minus 2 square dt. So if I do this integration, you can simply see that the answer is going to be just 4, right? Multiplied by 6 in here. Let me write it down for you. Okay. It's 48 divided by 12. It's going to be 4. I guess I passed the line. Sorry. Just that integration, the whole integration, is going to be 4, the final answer. It's very simple. And if you use the Parsevals, you would get the same answer, 4. Now, the last part of this question was to calculate the power in the output at the Y. And, in output signal Y, and to do that, again, you have two choices. You can use time domain or frequency domain, but unfortunately, I know I just have it here. So if you want to do in time domain, you have to square this wave and do the integration over cosines. You know, it's always difficult to do those kind of things. You have to do cosine square, 2 sine that multiplied by cosine. It's very difficult. So instead, if you look at the Fourier series of this is the Fourier series in compact form, right? You have only this guy and this guy, 2 terms. You can easily sum them up using Parseval's theory. That's why Parseval's theory is important for us. So I use Parseval's for Py. This was a good example to show you we can go back and forth between time and Fourier and use one of them, which makes things simpler for us. So Py, I use the compact form. Unfortunately, I erased in here, but you remember what was it, right? C02 divided by 4 plus 1 over 2 Cn2 and absolute. So in here, n goes from 1 to infinity. We have only 2 terms. Look at this. This guy and this guy. And 8 over pi squared plus 8 over 3 pi squared. And we have, this guy is 0 for this case. There is no C0. Okay? And if I do this calculation, calculator, this is 3.602. So you guys tell me what happened. The power, the energy, which was input to the signal, to the system was 4 watts. And then eventually I got 3.6 watt as my output. What happened to the rest?
Your C1 is wrong.
Sorry, what?
It should be 8 over pi, not pi over 8.
Which one?
C1. That one.
This one?
Is it pi over 8 or 8 over pi?
Pi over 8.
But then there you have an 8 over pi.
Ah, so my mistake. Should be vice versa maybe. Yeah. You please check. I assume that should be 8 over pi. Sorry about that. Yeah. Thank you. So what happened? You were telling me what happened to the power. What happened to the energy? Yeah, we filtered it out, right? So part of the energy was in the higher order harmonics. See, we just kept 2 harmonics, 1 and 3, and we discarded the rest. The rest had 0.4 watt energy, because this is the output, 4 was the input. Let me write it down in here again. PF was 4 watt, and P out is only 3.6. You know, energy cannot be destroyed, right? It should be always there, in somewhere. So when we lost 0.4, means that that energy was rejected, discarded. I mean, not rejected, it's reflected back to the source because of the feedback. Okay, well here I guess this talk, Parsival is done. I'm gonna introduce and talk about a new concept. Hopefully you have 10 minutes for it to make this. It's done. Any question? No? Okay. This is harmonic distortion, actually. I guess I believe it's 6, maybe 633. We call it harmonic distortion. It's a very important topic. Again, when you have, if you work with circuit, it's a very important topic. And what it really means is your system is not linear. If your system is not linear, which in actual life, your system, that H omega, you have signal as an input, and then you have a signal as output, YT. You learn how to do calculation for linear system, but no longer linear. Okay, if the system is not linear, your YT is not going to be only a coefficient multiplied by ft, but also it's going to have many other terms. I just keep this term to make it simple. But it's going to have a lot more. 3, 4, 5, 6, 7, 8, more. So why this is bad? Why we don't like this? I give you a very quick example. If your ft is pure signal, by pure means that it's only a cosine, it's only one harmonic. So if I take this and apply to this system, what I'm gonna get is a cosine plus b cosine of omega 0 t squared, right? That's what I'm gonna get. So if I do some simplification again, that's a trigonometric calculation, I'm gonna have this. Cosine of 2 omega 0 t. This is 2 omega 0 t. I hope you can see it. And you can see how ugly is this. You enter one harmonic signal to your system, and in the output you have, one single frequency, one tone signal has only one single frequency. It goes to your system, and your system generates a signal with double of that harmonic, double of that tone, and also a DC. So you know what's happening to the energy of the signal, which was initially stored in this signal? Now it's divided between 3 components. This is not wanted in your board. Your board designer, any board designer tries to avoid generating other harmonics. And unfortunately, this happens in real life. If you have a transistor, if you have A mixer, I don't want to use those technical words. I don't believe that any of you ever worked with mixer, for instance. But in future, if you continue in this field, you will see these words. You will get familiar with them. They will generate many harmonics. They are very nonlinear components. And this nonlinearity is a killer for us. We try to avoid them. So to give you a criteria to see that how nonlinear is a system, we need to define a criteria, a threshold, or maybe a quantity, it's a better word to say. When I give you a device, a system, you just need that number to decide if the system is linear or non-linear in real life. So that's we call it total harmonic distortion. And it's shown as TBH. What really it means that the power in the components which are coming after the fundamental frequency, so those CNs, you remember CNs, divided by the power in the fundamental signal. That's TBH. Anytime you like to calculate it, you do this. And we can simply write this like this. Okay? That's TBH. I give you a quick example. And you can find this example in your book. Okay. A power plant was supposed to deliver an output like yt equal cosine of omega t. Okay, this is what we wanted. However, it delivers another signal. Plus 1 over 25 cosine of 5 omega 0 t. Now this system is not linear because one frequency translated to 3 components. So what is TBH? Well, for this power plant, we calculate it. We just use that equation. Very simple. Harmonic 3 and 5 are unwanted signals. So the power in them is unwanted. We don't like them. And this is the wanted signal, the fundamental, right? If you do this calculation, it's going to be 1.39%. That's the TDH of this power plant. Because instead of providing a pure cosine signal, it's providing a pure cosine signal plus harmonics. Harmony means a coefficient multiplied by the frequency, right? 3 times of the omega 0. If I draw this for you, you will see what happened. If this is the Fourier domain, I call it n omega 0. This is at n equals 1. I see a strong signal, okay? And then at n equals 3, unfortunately, I see another signal 1 over 9. And then at n over 5, I see smaller signal 1 over 20. These two are unwanted signals. We don't like them because they are stealing from the power. This power plant could have more energy just in this arrow, in this component, if these two were not generated. So they're stealing from the actual power, the wanted power, and they are not useful. They are harmful kind of sometimes. So, any question?
So how would you deal with that particular curve?
Sorry again.
How would you deal with that particular curve in real life?
If you don't like them, how to deal with it?
How would you deal with it?
One way is to kill them by trying to minimize the nonlinearity in your system. look for those nonlinear and see where is the root of the nonlinear. But I promise you, it's very difficult to kill them all. But one day, just remove them from propagating inside your transition.